So when we're looking at our homework, let's hold on to it and let's go over it here. And I know that a lot of you tried to do it last night, and that's wonderful. And I know the power went out, so let's just move the deadline back a day. And we're just going to go ahead, though, and start covering it and just doing it together. And then you can fill it in as you go and whatever, and we'll just move on, okay? All right. So one of the things that, who noticed on page, well, let's start with page 8, right? Because that was the first page of the homework. Who can tell me what the steps of the scientific method are? Yep, go ahead. I'm sorry, say again? Ask a question, that's very good. That's right. So a lot of times what we do is we'll draw the scientific method the way you see there, where it's a flow chart, the arrows are going in one direction. In reality, it's a circle. So I'm going to draw it as a circle, okay, not, because that's how it really happens. And I'll explain to you, I think you'll understand better as we get to the end. So we're taking notes now, right? So you should, and by the way, you ladies, anybody with their back can turn around, you can move over here, you can move anywhere you'd like so that you can see the board and take notes. Don't feel like you're restricted when we're taking notes. So asking questions, usually how we start. I like to even start before that. I like to start with an observation. Somebody notices something, and then they ask a question about it. The famous example that I don't know if it's true or not, although there's a well, I'll tell you in a second, but have you heard of Isaac Newton sitting underneath the apple tree, and then the apple fell on his head? You heard that story? He said, oh my gosh, it's every time something goes up, it comes down, it falls. Then he came up with the theory of gravity. Have you ever heard that story? No. I learned it when I was a kid. I thought you might have. So, a sample of that tree, a clipping from that tree is growing at Case Western Reserve in their quad. You can go look at it as a little plaque. A clipping from Sir Isaac Newton's. Do you know who Isaac Newton is? Remember his laws of motion? Everything. Do you remember that? Isaac Newton's laws of motion, acceleration, velocity. Yeah. So he also came up with you've heard of the math called calculus? Well, he actually came up with calculus. So in order to describe motion. Calculus was invented several times in history. Isaac Newton developed it in Western culture. Calculus was also developed in Eastern culture, but in any case, he did. So you observe, you ask a question, just like he did. This apple fell on his head. He's like, why does it always fall? Why do apples always fall? Why don't they ever go up? Something's happening. And so he investigated and he came up with the law of gravity. And by the way, let's talk a little bit off to the side. What does it mean when you have a law? And it's one of those words that was defined. And then we have this word that we call a hypothesis. And then you have this word called a theory. And often people get these three confused. When we say a law, you and me, we usually mean, well, some rule, right, that somebody wrote out and said we have to follow. Does that make sense? Like, that's what we're used to with laws. And we try to apply it here, and often we don't. It doesn't do well, because what a law is a natural phenomenon. Do you know what the word phenomenon means? Okay, yes? If it's a happening, let's call it just a natural happening. Phenomenon means happening. happens. Something happens. That always happens the same way. This is my definition. So you can see that it differs from others. Whenever you read a definition, you have to try to put in words that you understand. Always happens the same way. So the reason we call it the law of gravity is because nobody's ever seen an apple go up by itself. Nobody's ever seen an apple fall up. Do you all agree? Except in the movies, obviously. Like apples always fall down. Things always fall down. Nothing ever falls up. So that's all a law is. It's not anything that we just observe it and we're like, wow, every time this happens, that happens. Every time. The law of conservation of energy. We can never create or you've heard of that one, right? Can never create or destroy energy and matter. You've never heard of that? No, you have. Good. So the reason that law exists is because we've never been able to make anything. We can change matter to energy. I can make heat. How do I make heat? I take the energy in paper and what do I do with it? Yeah. What do I do with it? There's energy in everything, right? There's energy in paper. How can I make this energy into heat? I'll wait for a second. When I'm waiting, I just want you to have a moment to think about it. Can I release the energy? How can I release the energy and heat? How much? There's a little bit of energy here, right? I hope we don't. Let's just hope we don't set off the fire alarm. I've set off the fire alarm 4 times working at this school. It's not my fault they are oversensitive fire alarms. Why do you gotta set so sensitive? A little bit of energy, yes? This paper has energy. How do I release it? Give a little bit of energy to the paper, just a little bit, and then what happens? Where is that energy coming from? It's not made, it's coming from the paper. So I have to turn off just so the fire alarm doesn't go off. Literally, you wouldn't believe the principals got all upset. Everybody's like, why are you sitting up? It's an experiment. What am I supposed to do? Not have experiments? How do you not have fire in a science lab? How does that happen? I mean, it's a science lab, right? All right. Anyways. So, in this example, this is the law of conservation of energy. Simply put, is we cannot create or destroy energy. All we can do is change it. We can change it from one form to another. And what some people will argue is, well, wait a minute, I can make a fire. So I'm going to go ahead and write that down. Make, in parentheses, a fire. Example. Well, what do you mean when you make a fire? What you mean is you have a fuel. In this case, it was paper that has energy. The fuel has what? A lot of energy. You agree gasoline has a lot of energy? Gasoline has more energy than paper, right? How do I know that? If I took the same amount of gasoline and I did that with that little flame and I put it near gasoline, what would happen? whoosh, right? It wouldn't just go Bernie, Bernie, Bernie. It would go boom, right? In your car, when you turn on your car, you don't hear, what do you hear? That's the little bit of gasoline exploding in the engine over and over and over again. So that's fuel. Fuel has energy. It has stored energy. It's very stable, relatively stable. So we have to, how do we release it? Well, in order to release it, we call this chemical reaction a combustion reaction. Do you agree? You've heard of this word? Combustion reaction? It's okay to say no. No? Okay. So combustion reaction is anytime you have a fuel and you add it, let me do it the way they do it. You add it to oxygen gas. Where are we getting oxygen gas? Am I going too fast? Where am I getting oxygen gas? The O2 is oxygen. That's what it stands for. The symbol for oxygen is an O. Chemical symbol for oxygen is an O. And oxygen gas has two oxygen atoms bonded together. We'll talk more about that later, okay? But that's what that is, oxygen gas. Where do we get oxygen gas normally? The air. That's right. We get it from the air. So oxygen gas is in the air. My pencil may have died. Oh, great. We get this from the air. And we have fuel, and then we just need a spark. Just need a spark. We need a little bit of energy, just a tiny bit of energy, to get all the rest out. So it's like if you're at the top of a hill and you're over here, you have this rock over here, and you're trying to get the rock over the hill. If you could get over that rock over to this place here, what's going to happen? If you get the rock here, what's going to happen to that rock if it's round? It's going to roll down, right? It's going to easily roll down the hill. But in order to get it up, you have to put energy in. Do you agree? Once you get it to the top, energy comes out. Is that making sense to you? See, anytime you have a chemical reaction, even a physical reaction, you have to put energy in, a little bit of energy in. If you put enough in, something happens. That's how chemical reactions work. Yeah.
What does that B word?
Put?
Oh.
Put? Sorry, when I'm writing quickly, I smash letters together. Put. Let me give some more space to this. Is comes out. Is that making sense? This is called, by the way, the fire triangle. And it's a way firemen try to train you into how to deal with fires. What do we do if there's a fire in the room and I get the fire extinguisher, what am I doing with the fire extinguisher? What part of the triangle am I impacting? So if the curtains start burning, what's the fuel? What part is the fuel? The curtains. Excellent. Where's the oxygen coming from? The air. And we already did the spark, so the ball's already rolling downhill. So we don't need the spark anymore because we already did it. It's burning. So now the ball's rolling downhill. How do we stop the curtains from burning? We use a fire extinguisher. What are we doing when we spray the fire extinguisher? How? What are we taking away? No, energy's there. Oxygen. We take away the oxygen by spraying it with the fire extinguisher. If you take away the oxygen, there's no fire anymore. You have a grease fire on your stove. What do? You're cooking your steak. Steak catches on fire. You got big fire. What are you going to do? You scream and run away. I get you. No, what? You could get a fire extinguisher, but if you don't have one, what are you going to do? No, never pour water on a grease fire. Do not pour water on a grease fire. What will happen is the grease will float away, and it's still burning, and the grease is going to float on top of the water, burning, and catch everything else on fire as it goes along. You'll spread the fire faster. You have a pan, the oil's on fire. What you going to do? Don't use water. Put the top on. It's easy. The solution is easy. You put the top on. What happens when you put the top on? What did you do? You got rid of the oxygen. Boom, fire's over. Okay, so getting rid of oxygen stops the fire. Why? Because you need all three of these things. You need the fuel and the spark. And once you get the ball rolling, if you take away the oxygen, the reaction stops. So that's a good example of why we say everything can be explained with this law, that we can't create or destroy energy. Okay. That's a law. Now, a hypothesis is a prediction. Yes, bless you. It's a theory. It's a guess. It's a guess. It's a scientific guess. It's a guess based on facts and logic. And it makes a prediction. A scientific hypothesis makes a prediction. So the simple way we write it, you can write it a bunch of different ways, but the simple way we write it, and you may have seen this before, is if this is true, whatever this is, right? It could be a whole sentence or whatever, then that will happen. Okay? If this is true, then that will happen. Well, let's look at this here. If it's true that you need oxygen to burn and I have a grease fire, then if I put a top on and get rid of the oxygen, the fire will go out, right? Then I'm making a prediction, correct? And then we can test it. It has to be testable. So if this, then that. So it's a guess. A hypothesis is just a guess based on logic. If everything falls down, then if I push Johnny off the roof, I'm just doing it so that you can laugh a little bit. Then Johnny will, he might die or not, but he's going to what? For sure. Fall down, right? If I push him off the roof and he falls up, then I'm wrong. But if I push him off the roof, he falls down, then I validated my hypothesis. Correct? All right. Is that okay? Everybody understand that? We're good with that? Is that good? If you have a question and you don't understand, you can say it. Feel free. I promise you, every question you have, anything you're confused about, there's probably 3 or 4 other people that are confused about it. And honestly, sometimes I'm confused about it. So please feel free to ask the question. Yeah.
Can you break down like the O2?
So you can understand the symbols. I shouldn't have put O2. I should just put oxygen. But I'm just used to writing O2. Sorry about that. So there's something called the periodic table. I'm going to give you a copy of it soon. Have you heard of that? Yeah. All right. The periodic table is broken up into columns and rows and has all the elements of life. It has gold and silver and it has uranium and iron and zinc and, all the elements that you could think. There's 100 and, last I checked, there was 119 elements. And there's you've heard, you don't need to draw this if you don't want to. This is just just a symbol you're going to see. When you see a periodic table, it's going to look something like this. One of those elements is this element called oxygen. An element, by the way, would anybody know what an element is? Anybody watch Airbenders? What did people used to think elements were? You've watched the Airbender cartoon, I'm sure, if not the movie. Huh? It's an anime show, and it's also, they have like a live action movie that sucked. But what's it? Have you ever heard of the Chinese elements, like the very basic elements of life? No. So in the Airbender show, they had fire, air, earth, and water, right? Fire, earth, air. That's actually based on, I don't know what you said, but it's being recorded, so be careful. Oh, yeah. No, they're elements. In ancient societies, we literally thought the elements of life were air, earth, fire, and water. If you look at Wiccan teachings, you know what Wiccans are? They're not really this, but let's just say witches, right? They're naturalists. They're like herbalists and stuff. They believe in a goddess and all that. I'm not sure the details of it, but in any case, you look at Wiccan culture and their belief system. What you'll find is they also believe in these fundamental elements, right? That's fine, because in the ancient cultures, they believed that. In fact, that's why when you had a fever in the Middle Ages, do you know what they would do to you? If you had a fever, you're really hot, do you know what they would do to you? They'd cut you and bleed you. And they'd drain your blood, so then you would get colder because they were too hot. They thought you had too much of the fire element. And so they got rid of that fire, and blood is red, so it's all in their head that all matches. And you did get colder, right? But you're getting colder because you're dying, so that's really not a good solution. But when you're looking at that, that's why they did what they did, because they were trying to get rid of that fire element. In a lot of ancient Chinese and Asian cultures, you still have. In a lot of the ancient medicines, you still have fire, earth, air, and water. And there's something else. They have a third element called qi, right? Have you heard of that, qi? It's kind of it's a power, right? But those are fundamental elements that they used to think. What we did is we started to break things down as humans. We started to say, okay, let's take this pair of scissors and let's keep breaking it down. So I'm going to cut it up into pieces. Cut up smaller and smaller. And when I get down to the fundamental part that makes up these scissors, I find out it's made of 3 or 4 elements. 3 or 4 things I can't break down any further. I can break this down, right? Give me something simple I can break this down into. 2 different things. Look at it. What can I break this down into? I'm not asking for anything scientific. What am I breaking this down into? Okay, razor, I guess. You can see the sharp part, right? But what is this sharp part made of? Metal. All right, so metal, and then what? And plastic. So easily I can separate the plastic from the metal, correct? But then I can break it up even further. This metal is made of steel and chromium. All right, so I can break this up into 2 elements. Iron, steel is made of iron, and then another element, right, called chrome. Okay? Plastic is made of carbon and hydrogen and oxygen. And I could break those are fundamental elements that the plastic is made of. I can't break oxygen up anymore. not an it stay oxygen. I could break it up, but then it's not oxygen anymore. Does that make sense? So what elements are things that they're the most fundamental things we can break down until we stop to lose the property of the substance. So when you have oxygen, oxygen is an element, and what it is has, if you broke it down really in this tiniest pieces, it has 8 protons and 8 neutrons in its nucleus, and then it has 8 electrons. You've seen this drawing before, I'm assuming? Something like it. I'm sure you've seen the drawing of an atom, right? Say what? Yeah, this is stuff you probably learned in middle school. I'm just trying to remind you a little bit, just kind of tying it all together. 2, 3, 4, 5, 6, 7, 8. So 8 total protons, 8 electrons. But we don't like to draw it that way. What we like to just do is just say, that's a lot of drawing. So we just write the word oxygen. So it's a single atom. Oxygen gas is not a single atom. It's bonded with another oxygen. So this one oxygen shares an electron with another. Oh, what's that? Oh, I see. I don't even know what's going on here. I didn't post the last one, the last class, because the last class's video just I had to update the app and it just caused all kinds of issues. So when I say oxygen, the stuff you breathe into your lungs that you use for living, the stuff you breathe into your lungs you lose for living, that's called oxygen, is actually 2 of these atoms that share electrons. They stick together. They're stuck. They're linked. They're bonded. We call it a bond because they're sharing electrons. I didn't really want to get into all this, but we do need to cover it, so I don't mind talking about it. Sharing electrons, we call that a covalent bond. So that covalent bond means you have 2 oxygens. Do you see that? One oxygen atom here and one oxygen atom there. And they're linked together. They're stuck together. It's really hard to separate oxygen. They're stuck together. In order to break them up and bond them to something else, you release a lot of energy. That's why there's fire and heat coming out of that paper. Because the oxygen in the air, you're breaking it up and recombining it with the stuff that's in this paper. And then you release the energy, and what do? You see fire, and you feel heat, right? That's energy. Energy is being released by this bond here, by this covalent bond. So you probably don't understand a lot of this. That's okay. I don't like jumping ahead like this, but just so you know, this is called a covalent bond. These are 2 atoms that are stuck together. And this is oxygen gas. And so what we do is instead of writing all that, we just say O2, oxygen gas. And then we put a little G for gas. Because oxygen can be liquid. Have you ever seen divers? Have you ever seen a scuba diver with a tank on their back? That tank has liquid oxygen in it. So we could take oxygen from the air and squeeze it and make it into liquid. So we put more oxygen in the tank. So when they go underwater, they can breathe the gas oxygen. It's interesting. But in any case, that's why we write it this way. There's oxygen, the element, 2 atoms of oxygen bonded together. The subscript means there's 2 atoms of O. 2 atoms that are stuck together. Is that making sense to you guys? I know it doesn't make perfect sense because I haven't explained it yet, but at least there's some idea of why I put O2. Is that okay? Did that answer your question, dear? All right. Let's go ahead. And so you're making a gas, and that's oxygen gas, and you need that spark in order to take that gas and the fuel. Then you're combining the oxygen with the fuel, and you're releasing the extra energy. So that's what's going on there. So hypothesis is a guess, and it's a prediction. It's a prediction and a guess. That's what predictions are, right? Isn't a prediction a guess? Is it going to rain today? I predict yes. It's a guess, right? I don't know. I'm not God. I can't tell the future. I don't know if it's going to rain. Am I going to get an A or a B in the class? I predict I'm going to get an A. But I don't know. I might have a bad day. Maybe I get a B. So predictions are guess, but they're guesses based on facts. When I guessed it was going to rain today, I looked outside, and it's really cloudy. And we just got done with some rain yesterday, and there's what's left of the hurricane is hitting the Carolinas, is moving its way up. That's going to bring more water. So I'm going to say, yeah, it's going to rain. But that's a guess. It might not rain, right? So I can make a logical guess based on the facts that are around me. Are we all good with that? Nobody should put anything away, because I do have an alarm set, just so you know. I do have an alarm set that gives us 2 minutes to put everything away. Okay? So unless something goes wrong with my equipment, we should be good. Any other questions? Okay, so then a theory. What's a theory? A theory is a tested hypothesis. If we test the hypothesis and then we find evidence that supports it, that says, okay, yeah, we're pretty sure that this is how it works. We're pretty sure that every time we throw something, that every time something falls, it falls down. Pretty sure that's how it's going to go. And it's going to accelerate every time something falls. In fact, the theory that explains gravity says that when something falls, it gets faster. It falls faster and faster, and we say increases velocity at 10 meters per second. 10 meters per second is a velocity. 10 meters per second every second. So after 1 second of falling, you're moving at 10 meters per second. After 2 seconds of falling, you're falling 20 meters per second. After 3 seconds of falling, you're falling at 30 meters per second. Do you see how that works? That's a theory, and that theory is pretty good. It works, and we call this the acceleration of gravity. This is called the acceleration of gravity. But that's a theory. The theory of that explains how things fall. So it's something it's an explanation. A theory is an explanation of a law. Our theories change all the time. Why do they change all the time? Because as we go on, as we learn more, we learn that our old theory just doesn't work anymore. It doesn't explain everything. So when we see new things, when we go new places, when we measure better, when we get better measuring devices, then we start noticing that, wow, our old way of thinking doesn't work. For instance, some people used to think the earth was flat. You look at the horizon, everything's flat. Maybe there's some hills, bumps and stuff, but it's pretty flat. That's what they're thinking. It might go up and down, but the earth isn't round. Why would you think the earth is round? That makes no sense. But as we got to go higher, as we went to the top of the mountains and we saw the curvature of the earth, as you start to see other pieces of evidence, then we started to think, wait a minute, the earth is round. our theory explaining how things work didn't work. For the longest time, we thought the Earth was the center of the solar system of the universe, correct? Did you remember that from middle school? We used to think that the sun went around the Earth. In fact, in ancient Egypt, they thought there was this guy named Ra, and a god, right? And he had a chariot, and he pulled the sun around the Earth. That's what they thought. Because they saw the sun, it looks like the sun's moving, isn't it? But today we know the sun stays still relative to our planet, and our planet is spinning and then revolving, right? But we know that because of experiments. So our theories have changed. Our explanations of phenomenon, our explanations of laws have changed as we've experimented, collected data, improved our measurement, our technology. Things have changed. All right. So that gets us through, I think, a lot of the questions that you had to answer, and I hope that helped. We still have some time, so let me finish drawing the circular version of the scientific method. So you have a question, you ask a question, and the next thing that you have to do is you have to go do research. Like how much would it suck if you were testing the theory of gravity, and you started testing, you spent your whole life testing it, only to find out that she already did all those experiments 10 years ago. And you just wasted your whole life. So it's probably a good idea to do some research and make sure that somebody else didn't already do what you did, whatever someone else might have learned. And then once you've done that, then you can construct an educated guess. Construct a hypothesis. And then the test, then we got to test with an experiment. So then we have to do an experiment if it's going to be science. And then analyze the results. Because just because you do an experiment and you get results doesn't mean you understand what it is that you got. Finally, you either accept the hypothesis, you think your guess was good, and you're going to go with it, or you reject the hypothesis. One of the two is going to happen. Then whichever one you do, whichever one happens, either way, you're going to report what you've seen. Report your results, including your conclusions. So that's going to lead you to ask more questions, isn't it? There's always another question. Always another question. So just because Isaac Newton found out that everything that goes up has to fall down, did you write all this down already, Darwin? You sure? Okay. You have your note. You just resting your arms on your book bag. So the results, you have results to ask questions, and that just keeps going round and round. So this never really stops. It never really ends. So I like this circular version more, but I understand why they put it like this, because it's easier to read, right, than this circular version. You can do it in a circular way that looks nice, but in any case, there it is. So let's go through these answers now that we've done this. Do we have time? I forgot one in this class. Let's see. this class can end at 47, and it's 40, so we got 7 minutes. So that's good. We can answer a lot of the questions really quickly. Why might an accepted hypothesis be rejected later? Yeah, based on what I just said. Why might you, if we accept a hypothesis today, and we call that, what's an accepted hypothesis? What do we call an accepted hypothesis? A theory. Excellent. So now we have a theory. Why might we reject it later? Yeah.
New findings?
New findings. Yeah. So we have new findings. And you probably had that same answer. I apologize. All right. So that's it. Explain why a method must be repeatable. Why must we have to repeat it? Can you? I know I didn't say that directly in what we talked about. Why might you have to repeat it? Yeah.
The method must be repeated because no matter how many methods you use, it will be more and better evidence and information.
Yeah, that's part of it. You're right. Now the other thing is you might have gotten lucky. Let's say you did an experiment and you proved that, you proved something. Yeah, like, yay, I proved it. I got it. My hypothesis was right. You publish it. But what if you just got lucky? What if I'm flipping a coin? I say every time I can flip a coin, every time I flip a coin, it comes out head. I'm good. And I flip it once and I get heads. Do you believe me? How many times do I have to flip it for you to believe that I can do it every time? Well, a lot, right? Mm-hmm. I have to repeat it a lot for you to actually start thinking, okay, maybe he can do it. So we repeat it to make sure that we didn't get lucky, or there wasn't a mistake, or that it is actually something that happens a lot, enough that we should think about it as a theory. Does that make sense? Okay. So in which situation is difficult, if not impossible, to control all the variables? Look at those 3 situations. One is in a laboratory. One is looking at a natural phenomenon, but you in a controlled environment. And the other is in nature. Which would be almost impossible to control all the variables? In nature. Because you're going to go in the woods, you can observe, but it could be a hot day, it could be a cold day. I can't control that, right? So there's a lot of things I can't control. All right. So the next, study the example above the features of cryptic. By the way, do you know what cryptic is? That means camouflage, like a chameleon. Cryptic is hidden, means hidden, okay? Study the example above illustrating the features of cryptic and conspicuous caterpillars. So caterpillars that are hard to see because they're camouflaged, and those that are brightly colored. You've seen caterpillars that are orange, right, and yellow and white, and others that are kind of green and they blend into the leaves, right? So caterpillars can come in different ways. And it says, generate a hypothesis to explain the observation. Some caterpillars are brightly colored and conspicuous, while others are cryptic and blend in their surroundings. Well, the bright colored ones want to be seen. Why do they want to be seen? I'm going to give you the answer because we're running out of time. So bright colored ones, they tend to be poisonous. And they're telling the birds, if you eat me, you're going to die. And so they crawl around. No bird eats them because they're poisonous. The cryptic ones, they take another strategy. If they blend in, they can't be seen. So both are survival strategies, but one is based on the idea that they want to be seen because that's going to help defend them. The other one is hidden because that helps defend them. Okay? 2 different strategies. That's the hypothesis. We're going to work on the null tomorrow, so don't worry if you couldn't answer the null. I know it's incredibly hard. In fact, I had a video I wanted to show you, but I felt that this conversation was more useful. What do you guys think? Was this one more useful? Did it help? Okay, so go ahead and try to answer the rest of this. Tonight, bring me whatever you have. It's okay that you don't have it right. Bring it tomorrow. Okay. hold on a second. Is that you take the signing sheet off and put it in your box, right? That's how we're gonna do. That's how we turn things in. By the way, excellent work today. Asking questions and participating. I'm gonna take attendance before we move on. Ali, are you here? Ali, Tulian is missing. Kaylee? Kylie, I'm sorry. Kylie. Alka is here, right? You're Alka, you're Kylie, right? Did I get that right? Kylie, okay. Bolden, are you here? No, absent. Brown, okay, very good. Raven, I saw her, I met her yesterday. I met two Ravens, though, yesterday's a problem. Raven, are you here? No? Oh, let me see your face. I'm trying to get your names. Raven, where are you? I can't see you. Oh, there you are. Okay. Drake is absent? Okay. Are you here? Oh, okay. So you guys have to speak up, guys. I can't see you. And you might be lifting your hand, but I can't see you. It's hard to see you when you're on stools and I'm sitting. Dunlap. Very good. Foster. Very good. Thank you. Smitry's here. I can't. You're going to have to help me with that. Seriously. Leah. I told you I'm bad with names. In my head, I got Spanish, English, French, and then all of it's all mixed. It's hard. Green. Henry. King. Ivan. It's my brother's middle name, Ivan. Frank. All right, there you are, Frank. Pritchett. It's not time to go. You might hear people in the hallway, but I haven't. Is it 47 already? Yeah. Oh, wait, you can go. Sorry, I don't know what we're on my. Jada. Here. If I didn't say your name, wait. Whitner. Whitsett. And then Wilson's probably absent. Hey, how's it going?
How you doing?
Good to see you, kiddo.
You miss me in your class?
Oh, no, you're not allowed to have an RTA pass.
No, why ain't I? Oh. You trying to tell my business in here.
You didn't get an RTA pass, did you?
She wasn't even on the RTA when it happened.
It don't matter. The whole ninth grade's been RTA'd off. Come on, that was good. That was good. Come on, you guys are matching. What's up with that?
Why you didn't make
trying
me
to be
your
like
TA?
Do you miss us being
Make
in?
me your TA.
I don't have TAs.
Oh, he ain't never
I
had
did
a
deal with. I did have TAs.
Do you miss us? Fourth period?
Yes.
Fourth period was the best. Fourth period really was the best class. I don't care.
Oh, just these pages.
I used to hit the study hall so I can
8, 9,
finish my work.
Oh, okay.
That's what you're doing. Okay, good.
Chanelli.
How's
You
it
take
going?
this class?
No. I was like, woo. Woo. Mendoza, you miss me taking your class?
RTA pass, did you?
He said the whole ninth grade.
Stop!
The whole sophomore class can't get your class
He
pass
said-
number because of what happened on the RTA.
Yeah.
Well, I got one.
Me
I wasn't
too.
on that.
He thought
but
that-
How you get one?
I'm being kidding.
Right, they should have never gave her
They
one.
didn't
It's like
pay me.
serious.
No,
It's like-
they should never gave her one.
Stop telling my business in front of these people.
Fighting on RTA is crazy.
Oh, you gonna pull that part? You gonna pull
I
that
didn't
part?
say nothing.
Right.
It was an inside joke. She can make it all public.
I'm about to leave because you got
I
second
gotta go
period.
to study hall.
Yeah.
Mendoza, my phone is dead. When I mean dead, I
You don't
mean
need
dead,
it?
dead.
My car was
You
on
need
last
to
night,
charge it?
Mendoza.
Huh?
Can you believe that?
You can't have it on anyway.
My young
got some
probably
candy?
on my car.
I just plugged in.
No, Mendoza.
I don't even have my coffee machine in. No
They got the
no
bed, they got the
drink.
microwave, they got the coffee machine, they got the TV. They got the bed.
Oh, they
I
freshman
took
year.
it to the other.
I forgot my pouch here yesterday.
Do your work.
And my phone and my book.
All right, give me the phone and get out of here. I have a class.
We gotta clean.
What they be learning?
I don't know, but you have
Biology.
I don't remember learning this.
You got to go to class.
I gotta